All right, welcome back to calculus. We're going to do a little bit more of the main idea we're going for with this section of calculus and less of exact numbers and formulas and notation and stuff. We're gonna focus on what's the big idea we're going for. Now you did learn summation notation, possibly for the second time or possibly for the first time, and why did we suddenly switch to that? Well, here's part of the reason. So there is going to be some notation in this, but it's mostly going to be the big idea, and then I'll go back and do a lot more of the actual notation, where that's coming from, and all that in other videos. So first, though, I want to give you the big idea. So we know how to calculate the area if of more simple shapes, more basic geometric shapes like rectangles. It's just base times height. In other words, in this case, 5 times 6 or 30. So that's fairly straightforward. Rectangles are very easy to work with. Something where so that's the area under a straight line that's has a constant value of 5. It starts at 5, it ends at 5, it's 5, all the way in between. So nothing changes. That's a very easy to shape to get the area underneath of. However, if for something a little bit more complicated, like this function here, it's the top part is not constant. This is a function here, and this is not as easy to calculate because you don't have a rectangle. So you would have to break it up into smaller shapes, and how do you know how to do that for each thing, for each section of it? I mean, if you cut it here, maybe you could get on to shape. You don't really know. So the main idea is we're going to start with the concept of cutting this section, this area we don't know. It's just called area, and we don't know what it is equal to. And we're going to take that area, and we really don't know what it's equal to, but what we can do is we can calculate the area of a rectangle very easily. So instead of just coming up with something really complicated for this, we're going to start with something simple and estimate it with rectangles. So let's look at what that looks like here. So it goes kind of up and kind of down, and then up a little bit, and then up again. So what the basic idea is, let's say, well, let's go with a different one. Let's say you had a set piece for your play, and it's something like this, some mountains, and you need it painted a certain color for the play, but it's really, really big, and you don't want to, you don't want to go out and buy 5 times as much paint as you need. In fact, it's so big that probably if you get slightly off with your area, you might end up buying a whole extra can that you won't use ever again. That'll be wasted money. So instead, so what you need to do is you need to estimate how much area you're actually dealing with, and paint cans have how much area that will cover on the label of the can. So one way you could do this is because rectangles are easy. So you might say, okay, well, let's look. If this is all one rectangle, the biggest rectangle we could have, take the widest point. This is our is our height, and then our width, our base is down here, and that will give me an approximation uh, of of the area of this. Now, of course, that's almost twice as much area as is actually in here. As you can see, there's a lot of wasted space up here that you're not actually going to be painting. So this is a huge waste um, of paint. So then you might think to yourself, well, let's look. Let's get a little bit of a better estimate. Instead of just doing one, how about, there's these one, two, and then kind of a third one of these little mountains. Let's see about how much of the mountain we can get. So it's about right here, and this one, is about right here, and then this last one is sort of like that. Or maybe I want to estimate it about here, or something like that. So now we have three different rectangles, and again, you're doing this. This is your first base and your first height, and then this is your second height and your second base, and this is your third height, 3, and this is your third base. And one of the important things to notice here is that if you add all these together, you get the base of the actual thing. So so that's one thing to notice is this would be a better approximation because we've eliminated, as you can see, this area up here that was kind of wasted, and we've eliminated this area up here that was wasted. So this is closer to an actual example. Now, if we actually want to get the area itself, or maybe somebody says, you know what, I kind of see where this is going. What if we just did a whole bunch of rectangles and put them inside so that we could be sure that it would be at least we need this much paint. So that would be something like this. Maybe you cut it up into, let's say, I don't know, a certain number of lengths and make them all the same instead of trying to get the general shape of the graph, or of the top. Just sort of say, all right, well, let's break it up into a certain number of equal distances, and then just see how high up these things go. And then you might try to pick the right height that makes the most sense. So let's say you're going for the lowest. We at least need this much, and there will be no wasted. And then maybe we'll go back to the store and get another little tiny can or something. So let's go for the lowest, for an underestimate. So let's see. Let's put it. We at least need this much. You remember, you're making it perfect rectangles, and then we at least need this much. And here, this one is on the lower side. Here, this one's the lower side. Dun, dun, and so on. And so, what are we doing here? Now, notice that this is actually tied to the actual specific points on the actual function. If this was a function, if let's say you knew what the formula for this was, these are actual y values. So f of, if let's say this is, let's say this is 3. This is actually f of 3 is is the height of this particular rectangle. And then let's say maybe this is from 3 to 4, then the width here would be 1. So you have, maybe this is 5, I don't know. So for right here, you have a little area, and we could label these area 1, area 2, area 3, area 4, and then I'm not going to label every single one, but this one would be the last one. Move that over. Let's say area N for the last one. That's still hard to see. AN. Okay. All right. So you have all these areas, and now this is an underestimate. What we can say is the area of the whole thing is approximately A1 plus A2 plus A3 plus all the way to AN. And now, again, we're gonna get into this a little bit more specifically. But you're actually using y values and x values to just calculate a box, and then you're going to add up all those boxes, and that'll give you an approximation for the area under the curve. This is extremely useful for just so many applications. This is the other major calculus topic is area. So let's see. This one was clearly and absolutely an underestimate. We also had some overestimates, and those hit sort of the top, and they went out. But what did you notice? I hope you noticed that the more boxes we had, the closer we got to the actual area, right? I mean, here we have about 10. When we just had one, it was horribly off. So even if we had an overestimate, if we had 100 different boxes, there'd be hardly any space in here. If we just had one, it would be very hard to pick the right spot for it to be even close. So one of the things to notice is that for more boxes, which means n is large, is a closer estimate. All right, so we're going to get into some details of what this looks like. Okay, let's do it right here. Okay, so I wanted to show you guys an overestimate as well. So let's say we have a similar one, a similar set piece that goes like this. Okay. And so this is the set piece. Notice we always have a beginning set point and an end point. You don't have an infinite set piece. That would take an infinite amount of paint. You're always going from a specific point to a specific start point to a specific end point. And you can always measure this distance. And one of the main things to notice is that these two numbers don't change as you put in more and more boxes. So what you're not doing is you're not taking the same size box and just putting more boxes on. What you're doing is you're cutting up the specific length of, let's say, I don't know, 15 feet into smaller and smaller pieces as the number of boxes gets bigger, right? So if you have one box, you're cutting it in half. Or if you have one box, you don't cut it in half at all. If you 2, you're cutting it in half. If you have 4, you're cutting it into even smaller pieces, and so on and so forth. If you have, 100, then each of these is cut into 25 more boxes, and that's really, 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 really close to being the exact area. Let's look at some. Let's look at an overestimate. What would an overestimate look like? All right. Well, um, let's say, now this is an easier example to show. We just start with this point, the left point, as our box height. So each point we choose has to be somewhere between these two things. Let's just choose the left side for this box. And then let's choose the left side for this box. And then the left side for this box. And the left side for this box. Now, do you see how each time, we'll call this a L, each time we have some area that's higher that we're including that we shouldn't include. And of course, it's getting smaller and smaller, but in this case, that is bigger than the actual area. And then let's try doing the opposite direction. Let's say, what if we choose the right side for this one? Yeah, and then the right side for this one, and then the right side for this one, and then the right side for this one. Notice how here, what we actually have is we're getting the area down here. And so there's a piece of the actual area right here that we're not getting for this right side one. So this is for sure less than the right side one in this case is for sure less than the actual area. So this is an underestimate, and this is an overestimate. Now, if you look at this maybe in a mirror, what you can see is if it was going the other direction, then what we would have is the left side estimate would be less than the total area, which would be less than the right side estimate. Or if you have, your set piece from over here, let's just fill that in here quick. Right, so your left side would be bigger, your right side ones would be bigger, and your left side ones would be smaller going this way. Okay. Or if you have something like this, notice we didn't consistently do it from one side or the other. We just did whichever side was smaller. If we consistently did it from the left, then for part of it, it would be over, for part of it would be under, and so it would be sort of a in between estimate. It'd be hard to say whether it's lower as one or the other. But one thing we could do is actually average the two, which is kind of cool. All right. So that's the basic idea of why we're using summation here, is because our approximate area is a sum. The sum from I equals 1 to n of a sub I, or the box that we make using x's and y's, and we're just going to have a bunch of them, and then we're going to add them together. So we're doing a whole bunch of boxes over and over again, but we're going to use algebra to do that really fast instead of having to add a lot of things. Okay, so let's see. So remember what this is, though, is this is the sum from I equals 1 to n. What was the base? The base was the change in x, and the height, you remember, was the y value. Oops. The height is the y value, so that's really cool. To f of a particular x value that we choose, x sub I. I'm going to show you this, explain this more in another video, but let's, each of these things that you choose, there's x1, x2, x3, x4, and so on, all the way up to xn, possibly x sub k or something like that, where you know, maybe you're not using the same number for these. But the point is, we have different x values that we're dealing with as well, and those are just, we just take that, plug it into the function, and get the height for each of our box. But we're doing that each time. So one of the things I wanted to show you guys was that we're not going to do a lot of the math in this video. No, we're not going to do a lot of the math in this video. I just wanted to show you the overview. And then the connection to or the big spoiler, the connection back to calculus, is that the area, if you want the area exactly, what you do is you take this, which is an approximation for a specific number of boxes, and you take, and the important thing here is this is constant. The delta x has to be constant for this to work. What you do is you take the limit as n goes to infinity of this, I equals 1 to n, of f of x sub I delta x. Okay, and this gives you the area exactly because you have infinitely many boxes that are infinitely precise then, to giving you the area. There's no error left over. And what this is this actually is the integral of f of x dx. Notice there's the delta x becomes a dx because it's infinitely precise, and the f of xi becomes just the function. But this is a specific area. Remember, we said that this has to be from a specific point to a specific other endpoint. So unlike with our indefinite integrals, this has a specific starting and ending point. Remember, even though the number of boxes goes to infinity, that's just the number of boxes between A and B. So you're cutting it up into infinitely many boxes. And again, in order to keep delta x constant, what you do is you take b minus a and divide by n. Again, I'm going to go over all the details in other videos. But again, if you have, let's say, I don't know, 4 to 13, and you want n to be, I don't know, 20, your difference, your width for each one would be 13 minus 4 over 20, which is 9 over 20. And what that does is, if you add this on to 4 20 times, you get 13. So that cuts, this is the way that you cut it into 20 perfect, perfectly spaced boxes. But the details aren't important right now. What's important is this idea that the integrals we've been doing are actually finding area, and yeah, we have a ways to go until we can do some of this. But this is called a definite integral because you're doing it over a specific interval uh, from a starting point A to an ending point B on a specific function, and you get a number as your answer. This is very different from an indefinite integral, where you don't do that. All right, I think I'm going to stop here because I'm getting carried away. We'll see how this goes.